Let's explore the fascinating world of microchip manufacturing, a process that combines cutting-edge technology, precision engineering, and microscopic craftsmanship. Inside your smartphone, there are dozens of microchips containing billions of transistors. But how are these incredible devices actually made? The journey begins in a semiconductor fabrication plant, often called a fab. These facilities are marvels of modern engineering, featuring clean rooms that span the area of multiple football fields. Inside, hundreds of specialized machines work in harmony, each costing anywhere from a few million to over $150 million. The manufacturing process is incredibly complex, taking about 3 months and involving around 1,000 distinct steps to transform a simple silicon wafer into hundreds of powerful microchips. At the heart of this process is the silicon wafer, a circular disc about 300 millimeters in diameter and less than a millimeter thick. This wafer serves as the foundation for building multiple layers of transistors and interconnecting wires. The manufacturing process can be broken down into several key stages, each requiring extreme precision and specialized equipment. The first stage involves creating the base transistors. This begins with the silicon wafer being oxidized to create an insulating layer. Then, using a process called photolithography, patterns are etched into this layer using ultraviolet light and special masks. These patterns define where the transistors will be placed. The process is similar to developing a photograph, but at a nanoscopic scale. Next comes ion implantation, where specific areas of the silicon are bombarded with ions to create the semiconductor properties necessary for transistors to function. This is followed by the deposition of various materials, including insulators and metals, to form the actual transistor structures. Modern transistors, called FinFETs, are three-dimensional structures that measure just a few nanometers across, thousands of times smaller than a human hair. After the base transistors are created, the process moves to building the interconnect layers. These are the complex networks of wires that connect all the transistors together. This stage involves repeatedly depositing layers of metal, usually copper, and insulating material, then etching precise patterns into them. Each layer must align perfectly with the ones below it, with tolerances measured in nanometers. The complexity of this process is staggering. A modern CPU might have up to 17 layers of these interconnects, each requiring multiple steps to create. Between each major step, the wafer must be perfectly cleaned and inspected for defects. Even a single dust particle can ruin an entire chip, which is why the clean rooms maintain air quality thousands of times cleaner than a hospital operating room. Throughout the manufacturing process, the wafers are transported between different machines using automated systems and special containers called FOAPs, front-opening unified pods. These containers protect the wafers from contamination and ensure they remain in a controlled environment at all times. One of the most critical and expensive pieces of equipment in the fab is the photolithography machine. These devices use extremely precise optics and ultraviolet light to project the circuit patterns onto the wafer. Modern photolithography machines use EUV, extreme ultraviolet light, with a wavelength of just 13.5 nanometers, allowing for the creation of incredibly small features. The manufacturing process also includes numerous testing and quality control steps. After each major stage, the wafers are inspected using sophisticated imaging equipment that can detect defects at the nanometer scale. This constant monitoring helps ensure that problems are caught early before they can affect the final product. Once all the layers are complete, the wafer undergoes final testing. Each individual chip on the wafer is tested for functionality, and its performance characteristics are measured. This information is used to grade the chips. Not all chips from the same wafer will perform identically, which is why we see different speed grades of the same processor model. The final stages involve cutting the individual chips from the wafer, packaging them in protective casings, and performing final testing. The packaging process is itself quite complex, involving the creation of electrical connections between the chip and its package, and the addition of features like heat spreaders to help manage thermal output. The entire manufacturing process requires incredible precision and control. Temperature, humidity, vibration, and countless other variables must be maintained within strict limits. The machines used must be regularly calibrated and maintained to ensure they continue operating within these tight tolerances. The economics of microchip manufacturing are equally fascinating. A single modern fab can cost upwards of $20 billion to build and equip. The complexity and cost of the process mean that only a handful of companies in the world are capable of manufacturing the most advanced chips. This has led to the concentration of manufacturing in specific regions and created interesting geopolitical dynamics in the industry. Looking to the future, chip manufacturing continues to evolve. New technologies like gate-all-around transistors and 3D stacking are being developed to push the boundaries of what's possible. The challenge of continuing to make smaller, more powerful chips while managing increasing manufacturing complexity remains one of the most important technological challenges of our time. The impact of microchip manufacturing extends far beyond the technology industry. These tiny devices power everything from smartphones to cars to medical devices, making them fundamental to modern life. Understanding how they're made helps us appreciate the incredible achievement they represent and the continued innovation needed to advance this technology further.